Hello everyone, welcome to another lecture of this series on fundamentals of structural analysis. So in this lecture, we're going to see overview of SFD BMD. In strength of materials, we do detailed understanding of SFD BMD, but here in this you can say series, I'll be giving an overview how we actually you can say find SFD BMD, or what is the you can say what is actually SFD BMD. So, so basically, we'll be dealing with, if I say write the full form of this SMD BMD is nothing but shear force diagram and you can say bending moment diagram, right? So we'll be dealing with shear force diagram and bending moment diagram, right? Bending moment diagram. So for now, the shear force and bending moment that we'll be finding out for a beam element or beam member. So suppose this is a beam, okay, and we have some support condition at the ends. It is a simply supported beam with one side pin supported, another side roller support, and we have some distributed load. It can be any kind of load. I'm just considering distributed load as of now. Some distributed load here, right? And due to this load, what will happen? The beam will deflect. Right? Due to this load, this beam will deflect. So basically, in this, you can say, in next few lectures, we'll be discussing the SFD BMD of beam elements. So what actually a beam element? It's nothing but a structural, what should I say? It's nothing but a structural element. So I will just write it is a structural element, okay, which generally resists loads applied to its axial axis, or you can say longitudinal axis. Longitudinal axis. Okay, so we'll be discussing the SFD BMD as of now for a beam element, which is a structural element that resists loads which are applied to its longitudinal axis, right? So as of now, we are assuming that beam is not taking any axial force, or beam is not having any axial load, right? So we can say assuming no axial force, no axial force or axial load, right? Okay, so what are the internal forces that will be developed when we'll be applying the load? Okay, it is resisting that load which is, you can say, applied transverse to its longitudinal axis, right? So the internal forces which will be developed, you can say, as it is bending like this, so there will be bending moment. The resisting force will be the bending moment. The internal forces will be basically bending moment and obviously the shear force. Bending moment and shear force. So these are the two internal forces we will be getting if we consider that the beam is only resisting the load applied to its transverse axis, and it is resisting by bending, right? So it is called flexural member, or you can say flexural behavior. So we'll be getting internal forces, bending moment and shear force. So now what generally we do, we can find out this bending moment and shear force. As it is an internal force, we need to cut a section somewhere, right? Because with this we will get the reactions only at the ends, but if you want to get the internal forces, we need to get a cross section here. We need to cut a section here, right? So suppose this is at a distance of xyz, whatever you write. So suppose it is at a distance of x from this point, and suppose I will name it as a and b. Okay, so at this point we will, suppose this is point x, we will get some internal force, and that will be in terms of bending moment and shear force. Now you can cut this kind of section you can say infinite number of section on this particular over the length of this particular beam, right? And every section the bending moment and shear force may vary. Okay, so when you want to have understand an overall behavior or overall you can say view of how the bending I mean how the beam is resisting the forces, so in this case you should get a you can say graphical representation of this internal forces, right? Okay, so you should get a graphical representation of this internal forces. So in this case what generally what we will be doing will be cutting section at every point or so at some interval, and we'll be finding out the bending moment. We'll see what is the pattern, right? So in here I will show you that you can develop an equation which will tell you what will be the pattern of the which will tell you what will be the pattern of this the bending moment at the shear force. Okay, how you will be graphically representing, so that will be defined by that equation, right? So uh, uh, to do that obviously we need to first understand the bending moment or shear force at one particular point. Okay, we need to find out a what should I say expression for that, and from that at any point of this particular beam we can find out the bending moment and shear force, and we can understand the you can say variation of the bending moment and shear force throughout its length. So when we say shear force diagram and bending moment diagram, so I would write it SFD and BMD are nothing but the graphical representation of the variation of internal forces along the length of the member. So internal forces along the length of the member. Okay, so we'll be graphically representing how the force is varying, how the internal force developed is varying throughout its length. Okay, so if we cut a section like this, but if we draw the you can say free body diagram of this particular beam. Okay, so what we will be getting, so suppose this is up to my x distance, here we had pin support, so we'll get this, let me draw it with a different color. We'll get a vertical reaction, suppose it is a point A, so AY, if we consider the axis like this, y and x. Okay, and we'll get this as AX, correct? We'll get this as AX. So and in here as this is my point X. Okay, so what will be uh, what we will get, we'll get the internal forces in terms of bending moment and shear force. So we'll get a shear force here, I will name it as Vx, and we will get a bending moment here which I will name it as Mx. We'll also get one more force which is the axial force, which we are saying that currently we are assuming it does not exist, assuming Fx equal to 0. So we are considering that this axial force is not there. Okay, fine. So similarly if we cut the other part, so this is the length up to x, the rest of the part if you see, so we had a roller support, so only vertical reaction we will get, suppose this is By, and in here we remember the internal forces. When we cut a section we'll get internal forces here at this point and at this point, and to you can say establish the equilibrium, because the if you want the structure to be stable we need to establish the equilibrium in this case, right? And in this case what will happen, the forces will be equal and opposite to each other, right? So in this case the shear force will be Vx and the bending moment will be this direction mx, and there will be opposite fx, right? So this will cancel each other. So ultimately it will be all the you can say summation of all forces will be 0. That means the system is in equilibrium, correct? So you can say, so this is the this way we find out the internal forces, right? This way we find out the internal forces. Now before jumping into further you can say calculation or understanding of this SFD BMD, we need to understand about the sign convention. We need to understand about the sign convention. Okay, so for algebraic equations, for, or you can say algebraic operations, not equations, for algebraic operations, the sign convention that we have considered earlier, the sign convention that we have considered earlier, it was something like this. Okay, upward reaction along x horizontal reaction and clockwise movement, these we have considered as positive. Okay, anything opposite to that we have considered it as negative. So this is for you can say algebraic operation. So when we'll be doing any mathematical operation to find out the internal forces, reactions, we'll be using this sign convention. But for to draw the bending moment and shear force diagram for BMD and SFD, the sign convention that we'll be following, the sign convention that we'll be following, what sign convention we'll be following? What sign convention we'll be following? So we'll be following a sign convention which is like this. Let me show you. The beam or any section which is, or any member which is bending like this, it is due to the moments which are like this, right? So this bending we consider it as positive and we call this as sagging. Okay, and if the bending occurs like this, okay, it is due to the moments like this, so we consider it as negative and we call it as hogging. We call it as hogging. Okay, so any positive value of bending moment we will consider it as sagging. Any negative value of bending moment will be considered it as hogging, right? And in case of shear force, if the shear force is, suppose this is the section and we are getting a shear force which is shear force couple which is clockwise. You can see this shear force couple is, these two forces are clockwise, it is creating clockwise moment, right? So this we will consider it as positive, which is clockwise. Okay, and if it is anti-clockwise, if the shear force couple is anti-clockwise like this, then we'll consider it as negative, so it is anti-clockwise. Okay, so from you remember from this that if it is clockwise then it is positive, it is anti-clockwise it is negative. If it is positive it is sagging, or vice versa. If it is sagging it is positive, if it is hogging it is negative, if it is negative it is hogging, if it is hogging it is negative, like that. Okay, vice versa you need to understand. So this is the sign convention we follow for the you can say SFD BMD. Okay, and this is the sign convention we follow for algebraic operations. So these are the two different sign conventions, and you should not get, you can say, confused in this particular. Okay, so let us understand with an example. Let us understand with an example. So we'll take a very simple example. Suppose the same simply supported beam I will consider example 1. So suppose we have a simply supported, sorry, draw it properly. We have a simply supported beam here with pin support and roller support here. Okay, and we have some load which is around 10 kilonewton per meter, right? Let me just write it here. It is 10 kilonewton per meter load, right? And this span of the beam, sorry, the span of the beam is 3 meter. Correct? Okay. So now if we draw the, you can say, free body diagram, so it will be like this. Here we have pin support. So AY, I will just name it. This is A, this is B. Okay. So AY, and we are considering the same axis. Horizontal is X, vertical is Y. So this is AX. Okay, and here we will get BY. We have a load, distributed load of 10 kilonewton per meter, right? So this is my you can say free body diagram, and this span is basically 3 meters. I will just mark this also. Now if you find out what we have done earlier from the equilibrium equations, we can say summation of Fx equal to 0. So it implies that Ax equal to 0, which is always true, right? Because there is no axial force applied, right? The beam is only taking the force which is applied transverse to its longitudinal axis, which we have already discussed, right? Summation of Fy, all the vertical loads. So we can say summation of Fy is equal to summation of Fy equal to 0. So it implies Ay plus By, whatever reaction we'll be getting, it should be equal to the load applied. So total load, it will be, you can say, 10 kilonewton per meter load applied over a 3 meter span. So 3 into 10, 30 kilonewton, right? 30. Okay, so we can say this is my, I will just mark it as this is the first equation. Then we can say summation of, suppose, moment about A, MA is equal to 0. So which implies, so what are the things that will generate moment here? If you see, this reaction By will create a anti-clockwise movement here. So anti-clockwise movement means negative as per our you can say sign convention for the mathematical operation, right? So we can say that Py multiplied by 3. So directly I can say, write it 3 Py, okay, minus, because it is anti-clockwise. Then this load will also create you can say moment, and the total load is how much? Total load is 30 kilonewton, and it is, when it is you can say distributed uniformly, so we consider that the point load, equivalent point load, it is acting at the center of this span, which will develop a moment, right? The lever arm will be half of this 3 meters, so it will be plus, as it is clockwise, load is 30 kilonewton multiplied by 1.5 is the half of this span, right? Somewhere here, okay, which is equal to 0. So from here we can find out the By, how it will be. You can see 30 into 1.5, so it is 45. It will go this side, so negative 45 minus 3 By equal to minus 45. So this minus minus will get cancelled, and By equal to will be getting 15, right? By will be getting 50. So this is one value we've got. So I will name it as 2. So from there you can easily find out Ay. Hence AY equal to how much? It will be 30 minus BY, so 30 minus 15. So AY is equal to also 15. From where? I can say from equation 1. Fine. So we got the reactions. Now, if we want to get what is the internal force developed, okay, what is the internal force developed? So in this case, we need to cut a section somewhere, right? So let us cut a section somewhere here, and let us say this distance is distance x. Okay, so I will just name this point at x. Okay, fine. So at x, now if we draw the free body diagram, so it will be something like this. Here we got AY. I will not draw the AX because ultimately it is 0 only. And here, what are the things we will get? What are the things we will get? We'll get a Vx. Now, I don't know what is the value of this Vx. So I'm just assuming that it is downward. Okay. Depending on the sign that you will be getting, depending on that you will be deciding what is the, you can say, how you will be, you can say, deciding the direction of the arrow depending on the value. So now you can say Vx, and we will get a moment like this, which is I am naming it as Mx. We are saying that there is no axial force, correct? And over this we have a load which is applied, which is 10 kilonewton meter, 10 kilonewton per meter. Okay, fine. So if you want to find out the Vx, how will be finding out? So very easily we know summation of Fy equal to 0, correct, which implies that Ay, okay, Ay, then we have this one, Vx. So it is downwards, so it will be minus Vx. Okay, downwards means minus Vx in as per our you can say what should I say, mathematical operation, you can say the sign convention. If it is downwards, then it is negative, so we are considering it is negative now. Okay, then what is the next load we have? If you see here, we have a load of 10 km per meter distributed over a length of x, right? So minus 10 into x equal to how much? Should be equal to 0, right? Should be equal to 0. So now from here, if you want to find out the Vx, if you see here, minus Vx equal to minus Ay plus 10x, right? So from here we can say Vx equal to Ay minus 10x. So Ay minus 10x. So what is the value of Ay? We know it is 15. So I can directly write it here. It is 15 minus 10x. So this is my expression for finding out the shear force at any point on this particular beam along its length. Okay, and if you understand, this is a linear equation, right? This is linear, so it can be, so what will happen, we understand from here that it will be linearly varying. Okay, right? So next, if we want to find out the you can say moment expression, so how will we finding out? Let us take summation of mx equal to 0, equilibrium equation, right? So which implies, so what are the things will generate moment? So you can see we have a mx here, okay, and here it is anti-clockwise, so it is negative, so minus mx. Then what will happen? This ay will create a clockwise moment, so it will be plus ay into x, ay multiplied by the lever arm is x, the length. Then this load will also act, I can say, at the center of this span, and it will also develop a moment here. So this load which is you can say spanning over a length of x. So the load is 10x, and it will be acting where? It will be acting where? At the center of this span, so it is x by 2. And what is the sign convention? So load suppose somewhere here, so the moment developed will be anti-clockwise, so it will be negative. So this is equal to 0. Correct? Now we know the value of ay. Again, it is 15x. So we can say minus mx plus 15x minus 5x square. Correct? Equal to 0. So from here we can say minus mx equal to minus 15x plus 5x square, right? And if we just take out this minus both sides, so it will be 15x and minus 5x square, right? 15x minus 5x square. So we got the expression for bending moment. And if you see here, it is now one order higher, and we are getting a quadratic equation here, right? And it says that from this equation or from this expression, what you understand, that the shape of the bending moment that we'll be getting, it is going to be a parabola. Okay, the shape of the bending moment that we'll be getting, it is going to be a parabola. So now what you can do, basically at any point you can find out the bending moment and shear force with this particular form. So our problem was like this. Our problem was like this. Okay, we had a load of 10 kilonewton per meter. Okay, this is A, this is B. Now if I just do it here, so this is 0, this is 3 meter span, right? Total is 3 meter span. So if I say, I will write it in a different color. So at x equal to 0, if I see, what will be the shear force? So you can see Vx equal to 15 minus 10x. So this term will be 0. So Vx equal to 15 kilonewton, or at x equal to 3, if I say this end 3 meter. So what will be the you can say Vx. So Vx will be, if you see here, 33 into 10, 30 minus 30 plus 15, so it will be minus 15. One more thing, I think I have written this wrong actually, 5x. So now if we so we got the, we can say, shear force at the two ends. Let us see what is the shear force. We know that shear force at the mid span, it should be 0, right? So if you say that at x equal to 1.5, what will be the Vx? So if you see here, 15 minus 10 into 1.5, that means it will be again 15. So 15 minus 15, 0. So we can say Vx equal to 0, right? So now if we, let me just take it up right there. So if I draw the go to shapes, line, draw a line like this. Okay, line like, so if we draw the shear force diagram here, so this is my beam. Okay, this is my beam. So we have at x equal to 0, it is plus 15, suppose. At x equal to 3, it is minus 15. I'm not writing the signs here. Okay, and at the center it is 0, correct? So, and the diagram will be like this. Just from the equation, so this is a linear equation and it is linearly varying. So this is my shear force diagram, correct? So at any point now with this particular formula, or you can say the expression that we have found out, you can find, you can say, shear force at any point on over this length of the beam. Okay, and now if we do for the moment, so this is my beam, this is my beam, correct? And we have 15x minus 5x square. So at x equal to 0, we see 15x, it will be 0 and 0. So mx equal to 0. So we expect the same, because this is a simply supported beam. At the end there will be no moment. At x equal to 3, if I say, so it will be mx equal to, you see, 45, 3 into 15, 45, minus 5 into 3 square means 9. So 45 again. So 45 minus 45, 0. So mx equal to 0. Let us make it at x equal to, at the center, at x equal to 1.5. What we will be getting? Mx equal to, so you can see 15 into 1.5 minus 5 into 1.5 square. So if I say 15 multiplied by 1.5 minus 5 multiplied by 1.5 square, so it is equal to 11.25 plus 11.25 kilonewton meter. Okay, this is kilonewton, this is in kilonewton meter, this is in kilonewton meter. Okay, so how the bending moment will be? So at the center is 11.25 kilonewton meter. At the end it is, so, and we know it will be a parabolic shape, something like this. Okay, it will be something like this. Now problem with this diagram is our bending is happening at the bottom of the beam, and this diagram, if you see here, we are writing the moment, okay, which is actually happening or occurring at the bottom face of the beam. The tension is happening at the bottom, right? But we are drawing the bending moment diagram in the compression phase at the top, right? So when we'll be, suppose we are designing a reinforced concrete beam, and we know that concrete structures are designed, or you can say when it is subject to tension, then these are more, for this we design basically. Concrete, if it is in compression, it is okay. If it is in tension, then it develops crack. So we, for that we design, we provide reinforcement. So now from this diagram, understanding the tension zone, it becomes bit, or what should I say, it is not in line with the bending. So bending is happening like this. I know the moment is at this 11.5 to 11.25 moment is actually here, but we are drawing it like this, right? So whenever in practice, whenever we'll be drawing the bending moment diagram, we always draw it based on this sign convention that we have just shown here. The positive is sagging, so we draw the bending moment also like this. Okay, so if it is sagging, we draw it downwards. If it is hogging, we draw it upwards. So the, the bending moment we should draw when working in a real life problem should be like this. Be like this, and here it will be 11.5 kilonewton. This is 0. Now this will give me clarity that okay, at the bottom face we have 11.25 moment, and for this I will find out the reinforcement I will provide here. So this AST, I'm just talking about it's RCC beam. For steel, compression is more. So this AST will be subject to this 11.25 kilonewton meter moment. okay, with this factor of safety and all, okay, and it is at the bottom phase. It is at the bottom phase, and we can say obviously from this diagram this is sagging. Okay, but from this diagram obviously we have all many of us have already done this way only, this sign convention only, but this will create confusion. This will create confusion, so it is always better to draw the bending moment diagram and the tension. Okay, so I hope it is clear. So you can see here now, if I just let me just before finishing, I have prepared one Excel with the same problem. Okay, let me show you the same problem. So what I have done, I have taken this formula. You can see 15 minus 10x, and for the bending moment 15x minus 5x square. Okay, so I have divided this beam from 0 to 3, okay, and at an interval of every 0.25 meters, right, from 0, 0.25, 0.5, like this, and I tried to replace the value of x with these values. So at 0.25, what is the value of shear force? At 0.5, what is the value of shear force? Like that I have found out up to the full length, and you can see at this end it is 15, in this end it is minus 15, and it is linearly varying, and from 0.25 you can see these values actually. Okay, if I see if there is any way of changing the chart type, let me see. Let it be. So here at 0.25, what is the value? 0.5. So you can see it is varying. It is 0 here, then it is getting a negative. It's changing the direction from here. Okay, fine. And if you see the bending moment diagram, as I drawn a parabolic shape, so the same way I have distributed from 0 to 3 at interval of 0.25, and I have replaced the value of x in the expression that we have found out, and we have found out the you can say values of moment at every 0.25 meters, and from 0 to 3 can say 0 and 3 meter it is 0, at the center it is 11.25, and for the other case it is you can say varying with this quadratic equation that we have found out. It is a parabolic shape. Okay, fine. So this way you can cross check also that whatever you can say you are drawing or you are making the bending moment and shear force diagram, whether it is correct or not. The thing is, from this what you are understanding. So this is the variation of the shear force. Shear force at the ends it is very at the maximum, then it is reducing, at the center it is 0, and then again it is changing the direction. The you can say it's just changing the direction, but the magnitude is the same at the end, right? Similarly for the bending moment also you can see the variation. So this is the graphical representation of your bending moment and shear force at any section of the particular beam. So from here, rather finding out at one section, from here you can easily understand, okay, I am getting maximum moment at the bottom. Okay, though we have drawn compression phase, but you can understand this is this is for sagging. So I am getting you can say, as it is positive, so it is sagging. Okay, so I am getting bending at the bottom, and for that I need to provide reinforcement at the bottom. So this is the understanding. Okay, understanding of the from the moment you can develop. Okay, so this is what we call bending moment and shear force diagram, is nothing but the graphical representation of the variation of moment and forces throughout the length of the member. I hope it is clear to all of you. So this is it for today's lecture. We'll see few more examples, because this relation we need to understand. Here we are getting linear and quadratic. We'll see in other loading conditions what is the expression, how the expression is being developed. Okay, whether it is the same or different pattern it is following. Okay, so this is it for today. We'll see you in the next lecture. Thank you.